Hi everyone. In this video I'm going to demonstrate a couple of one-way repeated measures analyses using IBM SPSS. Before we get started, let me note that underneath the video description you will find links to the data sets that I'm using as well as to this PowerPoint that is opened up, and the PowerPoint contains really a lot more detail than I'm going to cover in the video demonstration. So to begin, let's just address the question of what a one-way repeated measures design looks like in terms of the data setup. So basically the independent variable within this kind of design is referred to as a repeated factor, while the dependent variable is essentially referred to as a repeated measure. So here you can see in this screenshot we have a data set where each row represents a given person. And you can see right here I've just got a variable for subject identifier, and then you've got winter, spring, summer, and fall, and this is essentially based on the data set that I'm going to be illustrating shortly. So essentially these are Beck depression inventory scores for a group of for 14 individuals who are measured in the winter, spring, summer, and fall of a given year. So essentially then each person is responding to each level of the factor variable. The factor variable in this case is season or time. Now essentially within designs such as this, subjects serve as their own controls, and since the variability in the error term due to individual differences is removed as we were blocking on each subject, this generally makes these types of designs more powerful than randomized designs where subjects are randomly assigned to the different treatments. So for our first example, we will be using scores on the Beck depression inventory from a single group of individuals, as I just noted, and we're testing whether BDI scores vary across seasons within a one-year period. Just so you know, the data is based on a presentation by Pittick and Stevens from their 2016 text, and the main hypothesis is that mean BDI scores will vary significantly over the one-year period. If it is significant, then we will explore possible pairwise differences in means using Bonferroni adjusted pairwise comparisons. So here I've opened up the data set in SPSS. Again, each row represents a specific person or case. This is each person's subject identifier, and then their repeated measures in terms of Beck depression inventory during the winter season, spring season, summer season, and fall season. So to run our analysis, we're going to go up to Analyze, go to General Linear Model, and then Repeated Measures. And let me just go ahead and reset this. So where it says within subject factor name, this is whatever you want to name it. So in this case, I'm just going to name it season. And then number of levels refers to the number of levels for that repeated factor, which is 4. I'm going to click Add. I can give it a measure name for the repeated measurement, so I'll type in BDI for Beck depression inventory and click on Add. I don't have to do that, but I'm just kind of showing you what it's going to look like if you do. So I'm going to click on Define. And so over here, under within subjects variables, you've got 1, BDI, 2, BDI, 3, BDI, and so forth. So if I hadn't typed in BDI before, it just would say 1, 2, 3, and 4. So now I'm going to move my repeated measurements over to this box right here. We'll click under Options, and I will ask for descriptives, effect size. I can ask for power. We'll click on Continue. Under EM means, this is the estimated marginal means, and I'm going to click on both of these and move them over to the Display Means box. Now if I want to follow up a significant test result indicating that there is significant variation in the means over our repeated time points, then I can carry out Bonferroni adjusted pairwise or pair t-tests, and I can do that using by clicking on Compare Main Effects and then this button right here, and I've got Bonferroni selected right there. If I click on Continue, then I can continue on. Just so you know, if I click on Post Hoc, you'll notice that there's no option for Tukey's or anything of that nature. And that's because in SPSS, this is really only applicable when you have a between subjects factor with multiple levels. But in our case, we only have within subjects factor. So next I'll click on Plots and move Season over to the horizontal axis, click on add. So I'm just going to get a profile plot of the means at each level of our repeated factor. And if I want error bars like a confidence interval, 95% confidence interval, I can click on that as well. So I'll click on continue and then on OK, and then I end up with my output. So you can see I have, first off, you can see we have descriptive statistics, multivariate tests, then we have univariate test results with the associated sphericity test. Scrolling down below, you can see we have tests of within subjects contrast. This is useful for performing trend analysis. And then scrolling down a little bit further, you can see that we have our marginal means. So there's the grand mean as well as the means at each level of our repeated factor. And then we have our Bonferroni adjusted pairwise comparisons. And then further down, you can see we have our profile plot. So rather than going through all of this and making it a little bit difficult to read, I'm going to go back to my PowerPoint where I unpack the meaning of these pieces of output. So first off, under descriptive statistics, we see that the highest Beck depression inventory score was in fall, followed by spring, followed by winter, and then summer, the Beck depression inventory scores were the lowest. So when we move then to our multivariate test result, you can see actually we've got two sets of tests that we could evaluate whether there are differences in Beck depression inventory scores over time. There's multivariate test results, and then down here we have univariate test results. So the multivariate test, just like the univariate tests, assume independence of observations and multivariate normality. However, the multivariate test does not make an assumption, which is called sphericity, that the univariate approach does. And so I'll talk a little bit about sphericity shortly. Now there are times when the multivariate test may be more powerful than the univariate test. However, when sphericity is assumed, the univariate approach oftentimes will be more powerful than the multivariate test. So right here you can see with the multivariate test, there are actually 4 different test statistics, but they're, basically the tests are all giving the same information. Wilks lambda is probably the most commonly reported test statistic, and you can see that our p-value that's given is 0.127, which is obviously above a conventional level of 0.05. So we are going to maintain the null if we were using the multivariate test results and infer that there are no differences in BDI scores over the repeated measurements. Now, as I noted before, the standard univariate repeated measures ANOVA that you see kind of highlighted under the test of within subjects effects, it does assume a condition that's called sphericity. And so when sphericity is violated, there's an increased risk of committing a type 1 error. That is, that you infer that there are differences in the repeated measurement over time in this case when there are no differences. And so if sphericity appears to be violated, which we can use this information in this table above in order to kind of make that judgment, then one consideration might be to rely on the multivariate test results in order to make that judgment. However, there are adjusted univariate tests that you can use, such as the greenhouse geyser or Windfelt, that can kind of offset the effects of a sphericity violation. Now, formally speaking, sphericity refers to the structure of a covariance matrix of different scores. Basically, it assumes a diagonal covariance matrix where the variances of the different scores on the primary diagonal are equal and the covariances or correlations among those elements are 0. Now, we can kind of look at this sphericity a little bit more simply just by focusing in on the variances of the different scores. So let's go back into SPSS and compute them and then just take a quick look at the variances. So here we're back in our data set. So what I'm going to do is compute differences between scores in winter and spring, winter and summer, winter and fall, then spring and summer, spring and fall, and then summer and fall. So to do that, I'm just going to go up here to transform, click on compute variable, and I'll start off, I'll just call it diff1 if you will, and then we'll just say winter minus spring and click on OK, and so now you can see we have that difference score. Let's do another one. We'll do difference 2, and then we'll say winter minus the summer. So that'll be difference 2 right there, and then we'll do winter and the fall. So I'll just say difference 3, and we will type in fall right here, which is that variable there. So now when I look at the data set, you can see that now I've got difference 1, 2, and 3. And so now I've actually gone ahead and just computed the remaining. So there's actually 6 different scores. And just briefly, if we just go to Analyze Descriptives right here, and I move these different scores down to this box right here and just take a look at it, the standard deviations that you see over here, they're not differing all that much. And basically the variances are, the variance of any variable is essentially the square of the standard deviation. So there's not a whole lot of variation in those standard deviations across those different scores. So just keep in mind that the equality of variances of those different scores is a primary component of the sphericity assumption. But again, a little bit more formally speaking, it's actually assuming a diagonal covariance matrix with equal variances and then 0 as covariances on the off-diagonal elements. Okay, so the sphericity assumption can be evaluated using the Greenhouse-Geisser epsilon parameter that you see in the table above, and our Montys test. So starting off with the epsilon parameter, when it is equal to 1, this is considered an indicator that the sphericity assumption is met, and values less than 1 indicate departures from sphericity. So in the table above, our Greenhouse-Geisser epsilon parameter is 0.832, and basically this parameter is what is used to adjust the degrees of freedom in the repeated measures ANOVA, or basically the univariate ANOVA results, using a Greenhouse-Geisser adjustment. Now it's also worth noting that the Windfelt also has an epsilon parameter, which is this right here, and basically this one right here is a little bit more liberal when it comes to evaluating the presence of sphericity. So the Greenhouse-Geisser epsilon parameter tends to underestimate the degree to which sphericity is met, which makes it a more conservative estimate, whereas the Windfelt epsilon tends to overestimate the degree of sphericity, making it a more liberal estimate. Now if we look at Montys test, this is actually a test of sphericity, and so if it's significant, then we assume that sphericity is not met. And if it is not significant, then that would be an indicator that sphericity is met. So the p-value that's given right here is 0.408, which would suggest that sphericity is met. Now before I move on, let me just also note that if you have a situation where you have 2 repeated measurements, then in that particular case, there's no sphericity information that's going to be really provided. Basically, in the sig column right here, it will be empty, maybe with a little decimal, and then the Greenhouse-Geisser epsilon parameter will be 1. So there's no sense in really talking about the issue of sphericity when you only have 2 levels of the repeated factor. Okay, so Pittock and Stevens indicate that Montys test is sensitive to multivariate non-normality, and Field also highlighted the importance of considering the sample size when making judgments using this test. Basically, the test will be less powerful for detecting a violation of sphericity in smaller samples and overpowered perhaps in larger samples. So Pittock and Stevens suggest that Montys test is essentially unnecessary since the Greenhouse-Geisser test incorporates the degree to which data depart from sphericity in the test results. So they argue that when there is minor deviation from sphericity, then there's going to be a minor adjustment to the degrees of freedom, and when there's greater deviation from sphericity, then there will be a more substantial adjustment to the degrees of freedom when using the Greenhouse-Geisser adjustment in the context of the univariate analysis. Now, as we noted before, though, since the epsilon parameter that's computed by Greenhouse-Geisser can be overly conservative, which would make that univariate test overly conservative in terms of rejecting the null, then the Windfelt test provides a less conservative alternative to testing for differences in means. So as a general rule of thumb, if the Greenhouse-Geisser epsilon parameter is less than 0.75, then you can use the greenhouse geyser test. Otherwise, if you determine that sphericity is violated, or at least you are seeking a more conservative alternative to the standard sphericity assumed test, but a more liberal alternative to the greenhouse geyser, then you can use the Windfelt test, particularly when the greenhouse geyser epsilon parameter falls between 0.75 and 1. So for our data, the greenhouse geyser epsilon parameter was 0.832, so we're going to stick with the Windfelt test. And as you can see, from that, it looks like using that particular correction, we find statistical significance. So in other words, we would infer that there are significant differences in means on the Beck depression inventory across the repeated measurements. And hopefully by now you can see then that that it can easily be the case, or at least it's not always the case, that the multivariate test results and the univariate test results will yield the same conclusion. In our case right here, the multivariate test result indicated that there were no differences in means on the Beck depression inventory, whereas our univariate test right here actually is indicating that there are significant differences in means. Okay, so one question you may have is whether there's evidence of trending over time with respect to the means of the repeated measurements. So the test of within subjects contrast is a default contrast option that's printed out, and it can be useful in this regard to evaluate trending with respect to the means. So a linear trend implies that the change on the repeated measure will be the same between each pair of adjacent measurement occasions. A quadratic trend implies change in the change over time and will give the appearance of a bowl shape as there is only one bend in the line. And then a cubic trend assumes two bends in the line. So the highest possible trend is going to equal the number of repeated measurements minus 1. Okay, so and just really quickly, I just had to make a couple of corrections. So you might see a little minor change, but you can basically see when k is equal to 2, or the number of repeated measurements is equal to 2, the highest order trend that's possible is linear. When the number of repeated measures is 3, the highest order polynomial trend that's possible is a quadratic trend. And then when k is equal to 4, the highest order trend that's possible is a cubic trend. So when performing a trend analysis, as we're doing here, we need to look at the highest order polynomial terms that are significant, also consider the added explanatory power that results from the addition of terms, and perhaps also consider the shape of change itself, maybe through inspection of the profile plot. So I'll be honest, the trend analysis can sometimes be tricky. So although one rule of thumb might be to simply go with the highest order polynomial terms that are significant, it's also important to consider the value added of adding in those terms. Also consider the effect sizes associated with the candidate higher order terms, and consider whether the loss of parsimony is worth the cost of added complexity in terms of your ability to interpret the results, basically the trending. So you'll see right here in this particular table that the linear component is not statistically significant. The quadratic component would not be considered significant at the 0.05 level, but the cubic trend would be considered as statistically significant. If we look at the profile plot right here, you can see that it looks fairly consistent with more of a cubic trend. Okay, so for our remaining results, you can see there's this test of between subjects effects, which is not really particularly useful in the context of a single group repeated measures model. You can see we have estimated marginal means. There's the grand mean of depress. And then when we go to the next set of marginal means, you can see that where it says season, you can see these are the means that we actually had seen before. And then we've got our Bonferroni adjusted pairwise comparison. So these are basically paired t-tests with the p-values under the sig column right here that are adjusted for multiple comparisons. And it turns out that none of the pairwise comparisons are statistically significant. So returning back to our profile plot, you can see we had actually asked for 95% confidence bars for this particular plot, but it is worth mentioning that these bars in SPSS are formed as if there are no repeated measures analyses that are being carried out. So these are essentially the same error bars that you would get if you use the explore command and request 95% confidence intervals for each variable in the data set. So, and actually in Andy Field's text, he does a nice job of talking about this particular issue. Okay, so for our second example, we are going to be looking at within subject exposure to multiple treatments. So for this example, we will examine the effects of 4 drugs on reaction time. So we have data on 5 individuals who are exposed to all 4 drugs. The repeated measurement is itself reaction time, and this is also presented in the Pittock and Stevens text. And I do make a note that in research such as this, where basically the same individual is exposed to multiple treatments, it's important to control for possible order effects through the use of counterbalancing the administration of the stimuli. So otherwise what you'll have is time and order of administration being confounded. So counterbalancing can be accomplished by identifying all possible orders of administration of the stimuli and then randomly assigning participants to those orders. So here I have the data opened up in SPSS, and I'm going to go to Analyze, General Linear Model, and then go down to Repeated Measures as we did before. Up here where it says Within Subject Factor Name, what I'll call it is Drug. And then for the number of levels, we'll just say 4 and click on Add. I'm just going to leave the measure name alone for right now. So next, what I'll do is I'll highlight all of these and move them over to the Within Subjects Variables box. And then we'll go ahead and select all the previous options that we had selected before pretty much. So descriptives, effect size, power under options, under EM means, estimated marginal means, we'll select overall and drug, move them over. We'll compare main effects and select Bonferroni right here and then continue. Under plots, I'm going to move drug over right here and click on Add, and let's just say for this example we'll just select bar chart and we'll include error bars right there and then click on Continue and then on OK to get our results. So there's our multivariate test again, our univariate test results. The test of within subjects contrast is pretty much irrelevant in this context because basically the levels of the repeated factor are not ordered, so we can't really look at any kind of trending on that. So as we scroll down, you can see we have our pairwise comparisons, and then we have our profile plot. So looking at our output, you can see that the drug producing the highest reaction time is drug 4 right here, then followed up by drug 1, then drug 2, and then drug 3 right there. So the multivariate test results, you can see looking at our information related to Wilks lambda, you can see that there are significant differences in reaction time across drug conditions. So here our Montys test is not significant. However, the sample size was very low, and so the greenhouse geyser epsilon parameter was 0.605, which does suggest a more marked departure from sphericity. So if we were going to interpret the univariate results, we'll use the greenhouse geyser adjustment. And you can see right here that we have evidence again of statistical significance concerning reaction times across the drug conditions. So looking at the Bonferroni adjusted paired t-test, we see that there are 2 significant pairwise differences in reaction times. Basically, reaction times of participants when they were receiving drug 1 were 5.6 points lower on average than reaction times when they received drug 4. And then reaction times of participants when receiving drug 3 were 16.4 points lower on average than when they received drug 4. So here you can see our bar chart again, and this again is containing those 95% confidence intervals that are essentially formed as if there had been no repeated measures analysis that was carried out. So do keep that in mind if you're interpreting these. Now before I round this out, let me also note that under the menu option, under repeated measures, you do have an option for contrast. So if you want certain planned contrast, you can do that using certain kind of canned options, if you will, in SPSS. The default, as you can see, it's already set at polynomial, and that's where we were getting that trend analysis information. If we didn't want to use that, let's say we wanted to use simple contrast, you would basically identify a reference categories. The default is last. Let's just make it drug 1. We'll click on change right here just to show you. Click on continue and then on OK. And so all of this information is the same, but now as we kind of scroll down to our tests of within subjects contrast, which is right here, you can see right here we've got drug, you've got level 2 versus level 1, level 3 versus level 1, and level 4 versus level 1. So you have basically these three comparisons that are given. There's the p-values for each of those. So basically these comparisons involving level 3 and level 4 versus level 1, both of those were statistically significant. Okay, so that concludes this video presentation, and I appreciate you watching.